Good evening. Today I'm going to finish up the example problem about Stonecutter Company that has been left over from last class. So I believe you are required to answer the question number 10 this time, right? Okay. So the number 10 is, I think to answer both number 10 and 11, we need to construct a dual LP, right? Okay. This is the primary LP problem, right? The primary LP is maximization problem, and it has 4 decision variables and 3 constraints, which means in dual problem we will have minimization problem and 3 variables and 4 constraints, right? Okay. So the dual is minimization problem, and let's use y variable as a dual variable. So we will have 3 dual variables, y1, y2, y3, right? And because in the primary problem, the right-hand side values as 300, 180, and 300, transpose of this vector becomes the objective coefficient in the dual problem, right? So it's 300, 180, and 300. Is it too small? Okay. And we will have 4 constraints. The objective coefficient in the primary problem becomes the right-hand side value, the dual problem. So it is 280, 40, 500, and 510, right? And the constraint coefficient, the primary problem, actually the transpose of constraint coefficients becomes the dual constraint coefficient, right? So it's going to be 30, 20, 0, and 5, 8, and 20, 45, 60, 0, and 60, 30, 120, right? And because the primary LP is a maximization problem with less than equal constraint and greater than equals variables, non-negative variables, it is the form of primer in the symmetric primer dual pair, which means the dual must be a minimization problem with greater than equal constraints and non-negativity restrictions for all the variables, right? So this is the dual problem. So the question number 10 is the number of variables in the dual of this LP problem is just 3, right? And the sign restrictions on the dual variables are all non-negative, right? And what about number 12? The value of the second variable in the optimal dual solution is what? To answer this question, we can use duality theorem, right? You remember what it was? The duality theorem tells us the simplex multiplier vector pi relative to the basis is an optimal solution to the other side of the problem, right? And window provides dual price instead of dual variable. And what was the dual variable? Dual variable represents the rate of change of the objective function value with respect to the corresponding right-hand side values. Okay? And this dual variable is also called simplex multiplier. Okay? Which is represented by pi, right? And because the improve means increase the maximization problem and decrease the minimization problem. So in the maximization problem, this dual price is equal to the dual variable. Okay? However, in the minimization problem, dual price is what? Negative sign of dual variable. Okay? And currently, the dual prices for the first and second, third constraints are 6, 5, 0. Okay? What does it mean? Because this primer problem is maximization problem, right? This dual price is exactly the same as dual variable, which is simplex multiplier vector pi. Okay? That means first dual variable has a value of 6. Second dual variable equals 5. And third dual variable is 0. Okay? Does that make sense? So the number 12, the value of the second variable in the optimal dual solution is 5. Okay? Okay, then what about number 13? The value of the optimal objective value of the dual problem is what? We have dual problem, right? And we need to use these y values from question number 12. Okay? So our dual objective function value would be 300 times 6 plus 180 times 5 plus 300 times 0. What is this? 1800 plus 900, which is 2700. Okay? Does that make sense? Okay, then today let's reconsider the golf bag example, which has been covered earlier this semester when we are talking about graphical method for LP. Do you remember this example? Okay, so in this example, Par Incorporation manufactures standard bag and deluxe bag. Okay? And each bag produced requires 4 operations with the following processing times. And the plant manager estimates this following time will be available for the production of golf bags during the next quarter. And each standard bag contributes just $10, and each deluxe bag $9. And the company wishes to determine the number of each type bags, which will maximize their profit. Okay? And because the primary decision is how much of each golf bags should be produced, we have defined X variables like this. X1 represents the number of standard bags produced next quarter, and X2 is the number of deluxe bags produced. Then the complete LP formulation would be like this. Our objective is to maximize profit while at the same time satisfying the time restrictions for each 4 departments, right? Cut and dye department, sewing department, finishing department, and inspect and packing department. And I've got this LP formulation from Lindo. You remember? Lindo assumes every decision variable used in the model is non-negative. So the non-negativity restriction has been omitted this time. And if you use Lindo to solve this LP problem, you may obtain optimal solution like this, including reduced cost and dual prices, and the objective coefficient ranges and right-hand side ranges, and the final optimal Tableau. Okay? Of course, we are going to use all of these informations to answer the following questions. Okay, so the number 1, if the profit on standard bags were to decrease from $10 each to $7 each, what will be the effect on the number of standard bags to be produced? So what Lindo output we need to use to answer this question? Objective coefficient ranges, right? Okay. So the unit profit of a standard bag has been decreased from $10 to $7, right? And this changes means a decrease of $3 in the objective coefficient of the variable x1, right? So we need to look at the objective coefficient ranges. According to our Lindau report, the allowable decrease of x1 variable is 3.7, right? So how would you conclude? Okay. Right, no changes at all, right? Because $3 of decrease is less than the allowable decrease of 3.7 in the objective coefficient ranges, which means that the basis will not be changed. Okay? So, in that case, the number of standard bags to be produced would remain the same. Okay? Okay, next, number 2. If the profit on deluxe bags were to increase from $9 each to $15 each, what will be the effect on the number of deluxe bags to be produced? So, the unit profit of deluxe bag has been changed from $9 to $15, right? Which is an increment of $6, right? And the objective coefficient of x2 variable. And according to our Lindau report, the allowable increase of x2 variable is 5.285714. So what can you say about this? Yeah, the basis will be changed, right? Because the $6 of increase exceeds the allowable increase limit of 5.285714, which means that the basis will be changed, right? So the answer would be the number of deluxe bags to be produced would be changed, and specifically it will be increased, right? Okay, then what about number 3? The LP problem has exactly one optimal solution, or exactly two optimal solutions, or an infinite number of optimal solutions. Which of these are correct for our LP example? Earlier this semester, you've learned how to determine whether the current basic solution is feasible or non-feasible, optimal or non-optimal, or if the current LP is unbounded, things like that. From the simplex Tableau, you remember that? And Lindau provides the final optimal Tableau, which is this. So this is the optimal Tableau, which looks much more familiar to us. Okay? But basically it's the same. Okay? However, one very important thing is you need to change the sign of each objective coefficient, because Lindo provides this final Tableau based on G value. Instead of negative G. Okay? Because G value is 7,668.012, negative G should be equal to negative 7,668. Likewise, all the objective coefficients must have negative sign. You know what I'm talking about? If the given RP's objective function is, let's say, maximize x1 plus 2x2, for example, what Lindo output provided is set the objective function value equal to z, or not this side, okay. Sorry, with given maximization problem, x1 plus 2x2, Lindo set the objective function value equal to z. This side would be better. And then move x1 plus 2x2 to the left-hand side. So z minus x1 minus 2x2 equals 0. Okay? And then Lindo made the Tableau based on this. So it looks like G column, x1, x2 column, right-hand side columns, right? The objective coefficient for G variable would be 1 and negative 1, negative 2, 0, right? And this is slightly different from what we've done so far. What he did is, for a given maximization problem, x1 plus 2x2, we'll set the objective function value equal to z. Okay? And then move z to the left-hand side. Negative z plus x1 plus 2x2 equals 0. And then made the simplex Tableau based on this. So we have negative z instead of z. x1, x2 column, right-hand side, 1, 1 is 2, right? 0. Okay? I will use this way because it is much more makes sense to think of reduced cost or the relative profit. Okay, then let me ask you, is this optimal Tableau? We are dealing with maximization problem, right? So there is no positive relative profit, right? So this is an optimal Tableau, right? And because the coefficient of both slack 2 and slack 4 variables are negative number, which means the objective function value will be decreased. as you increase either slack 2 or slack 4 variable. Is that right? So everyone following me, right? So based on our current Tableau, the objective function looks like this. Maximize 0 times x1, 0 times x2, negative 4.375 times slack 2 plus 0 times slack 3 plus negative 6.937 times slack 4, 0 times slack 5. Is this correct? So obviously, if you increase, for example, slack number 2 by 1 unit, then the objective function value will be decreased by 4.375, okay? Which is not desirable. Okay, and currently the non-basic variables are slack 2 and slack 4. Is that right? So their value must be 0. And of course, the current Tableau, current basic solution is not infeasible, right? Because all the basic variables has positive values. I think I need to use. And because we know this is an optimal Tableau, next you need to decide if it has an infinite number of optimal solutions or exactly one optimal solution. Okay? So how do you know if it has an infinite number of optimal solutions? You remember? If the relative profit or the reduced cost of any non-basic variable is 0, then we may say that we have an alternate optimal solution. In our Tableau, there is no non-basic variables with a 0 relative profit, which means the current LP problem has exactly one optimal solution, right? Suppose if the relative profit of slack 2 is 0, for example, then increasing slack 2 variable from 0 will not affect on the objective function value, right? So we will have same objective function value with different sets of basic variables, okay? So in that case, we will have infinite number of optimal solutions. I just want you to refresh your memory. Okay, what about number 4? If an additional 10 hours were available in the inspect and packing department, what happened to the profit? The plant manager knows 135 hours are available for inspect and packing during the next quarter, right? And the row number 5 represents the time constraint for inspection and packing. So what happened to the objective function value? If an additional 10 hours were available, if the right-hand side value is increased by 10, then what happened to the optimal objective function value? So what information you need to look at? Right, both of them, right? Basically, we need to look at the dual price. But however, dual price remains valid only within the allowable right-hand side ranges, right? So we need to look at the right-hand side ranges. Increasing 10 hours for inspection and packing is within the allowable increased limit of infinity, right? So the current dual price for row number 5 are valid, okay? And the dual price for row number 5 is 0. So what is your answer? If an additional 10 hours were available in the inspection and packing department, the company would be able to obtain an additional $0 in profit, right? No changes, right? What about number 5? If an additional 10 hours were available, the cut and die department at this time, what happened to the objective function value? Row number 2 represents the time constraint for cut and die department, right? And currently, originally, 630 hours are available for cut and die department. So just like what we did in question number 4, we need to use dual price and right-hand side values, right-hand side ranges, right? Okay, here the dual price is 4.375087, which means the objective function will increase $4.3750 per additional hour of cutting and die department. So if an additional 10 hours were available, the cut and die department, the company will have an additional 10 times this much in profit. Is this correct?
I have a problem about the previous question.
Uh-huh.
So the profit will not change. The previous question.
No additional profits.
So I was thinking like it's like when you increase the number of hours, it's like increasing also the slab variable in that hole. No. Increase is like decreasing the slab variable.
Yeah, decreasing slab variable. Uh-huh.
It means that we are decreasing the slab variable.
Right. Right.
Slab number 5.
Uh-huh.
So
if you look at the final Tableau in that case, and you need to deal with substitution rate, right?
yeah.
But eventually it will come up with the same solution, right? Okay. That's a good question. So anyhow, it's too early to make a conclusion, right? Because we didn't even check the right-hand side ranges at this time, right? Because the dual price is meaningful within the allowable right-hand side ranges, right? So we need to check if the 10 hours of increase is within the allowable increase limit for row number 2. Yes, it is, right? So increasing 10 hours of cut and die department is still within the allowable increase limit of 52 hours. Okay? So the current dual price for row number 2 is still valid. Okay? So now you are safe to say that if an additional 10 hours were available for cut and die department, then company will have an additional 10 times $4.37 in profit, okay? Which is $43.75. What about number 6? Okay, so number 6 is which of the following is equivalent to increasing the variable slack 2? So we need to consider the row number 2, right? Which represents the time constraint for cut and die department. Again. And by introducing slack variable, we will obtain equality constraint, right? Which is 0.7 x1 plus x2 plus slack 2 equals 630, right? Okay, now what is the question? If slack 2, okay, so in that case, slack 2 is the unused hours, right? In the cut and die department, right? If this slack 2 were increased by theta, for example, okay, plus theta, then this equation becomes 0.7 x1 plus x2 plus slack 2 equals 630 minus theta, right? I just move theta to the right-hand side. Then we will have this. Is that correct? So this means more unused hours means fewer hours used. Does that make sense? So we may say that if the variable slack 2, which is the unused hours for cut and die department, were increased, this would be equivalent to decreasing the hours used in the cut and die department. Okay? So the answer is first one, right? Any questions so far? It's not too fast, right? Whether it's too slow? Okay. Let me know. Okay. Okay, what about number 7? If the variable slack 2 were increased by 10, what will be the effect on the production of standard golf bags per quarter? So, what information you need to look at? Substitution rate. Excellent. So, we've learned substitution rate alpha, ij, indicates how much xi, that is the basic variable, decreases as non-basic variable xj increases, right? And from the Lindo output, the substitution rate of slack 2 variable for standard golf bag, which is x1 variable, is negative 1.25. Is that correct? Which means as slack 2 variable increases by 1, the basic variable x1 decreases by negative 1.25, which means as slack 2 increases by 1, the basic variable x1 also increase by 1.25. Does that make sense? So, if slack 2 increases by 10 units, then the basic variable x1 will increase by 10 times 1.25. Is that right? So, if the slack variable slack 2 will increase by 10, then x1 would increase by 12.5 standard golf bags, right? Excuse me. Okay, what about number 8? If the variable slack 2 were increased by 10, what is the effect on the production of deluxe golf bag? Okay, this question is about the same as previous one, question number 7. So again, we need to look at the substitution rate of slack 2 for standard golf bag, which is x1, right? No, we need to look at deluxe golf bag, right? Sorry. So we need to look at x2, which is 875, right? So, as slack 2 increases by 10, the basic variable x2 will decrease by 1.875 times 10, right? Which means the production of deluxe golf bag would decrease by 18.75 deluxe golf bag. Is that correct? Okay. Okay, what about number 9? If a pivot were to be performed to enter the variable slack 2 into the basis, then according to the minimum ratio test, what will be the value of slack 2 in the resulting basic solution? So to answer this question, we may use optimal Tableau provided by Lindo or this Tableau, okay, which is the same. So if slack 2 enter the basis, we need to perform the minimum ratio test, right? And because this is the only one with non-negative value, right, in that pivoting column. So definitely the minimum ratio occurs at 251.998 over this substitution rate, 1.875. Okay? Which is, in my calculation, 134.4. Okay? That is, the value of slack 2 in the resulting basic solution would be approximately 134.4. That is the ratio of right-hand side and substitution rate. Okay? Any questions? Okay, next is number 10. If the variable slack 2 were to enter the basis, then which variable will leave the basis? So according to the minimum ratio test, because there is only one positive substitution rate in the row in which x2 is basic, this row must be the pivot row, right? So x2 variable should leave the basis. Okay? Okay. Then what about number 11? If the profit on standard bags were to decrease from $10 each to $6 each, what will be the effect on the number of standard bags to be produced? I think this question is very similar to question number 1 and 2, right? So we are dealing with a decrease of $4 in the objective coefficient of the variable x1, which means you need to look at the objective coefficient ranges. So according to our Lindo report, the allowable decrease of x1 variable is 3.7. And the $3 of, no, is $4, right? $4 of decrease from 10 to 6 exceeds the allowable decrease of 3.7, which means the basis will change, right? So the number of standard bags to be produced would decrease. Okay? Okay, how about number 12? I think, again, it's the same type of question, right? If the profit on deluxe bag were to increase from $9 to $13 each, what will be the effect on the number of deluxe bags to be produced? So we need to use objective coefficient ranges, right? And the allowable decrease, allowable increase of X2 variable, right? That is 5.28. So the $4 of increase is less than this allowable limit. That means the basis will not be changed. So the number of deluxe bags to be produced would remain the same. Okay? Okay, what about number 13? I think this question is also similar to questions number 4 and 5, I believe. So originally, 600 hours are available for sewing department. Right? Then what happened to the objective function value if the right-hand side value is increased by 10 hours? So in that case, we need to look at the dual price, right? And the right-hand side ranges at the same time. First, let's look at the right-hand side ranges. So increasing 10 hours of department is still within the allowable increase limit of, or is it, I need to look at the right-hand side ranges instead of objective coefficient ranges. It's infinity? Okay. Sorry, I have a lot of papers with me. So the allowable increase limit is infinity, right? Which means the current dual price for that row is valid, right? Next, we need to look at the dual prices for row number 3, right? Which is 0. So the profit would remain the same, right? So, isn't that easy? Right? I tried to give you lots of examples about the same type of questions. So I believe at this time you are feeling pretty confident with yourself about this topic, sensitivity analysis. Okay, what about the next question, number 14? Is another similar question, right? If an additional 10 hours were available in finishing department, what would be the company's profit? So originally 708 hours are available for finishing department. And you need to look at the right-hand side ranges. For row number 4, and increase limit, which is 192, right? So increasing 10 hours of finishing is still within this allowable increase limit, which means the current dual price for row number 4 are still valid, right? And here, the dual price is 6.93 for row number 4, right? Which means the objective function will increase $6.94 per additional hours of finishing department. Okay? Isn't it very easy, right? And actually, I plan to cover another example, which is about steak sauce example, but I don't think I have enough time. So I will stop here for today. Next time I will give you another 2 example problems for sensitivity analysis. And I believe that will be the last exercise problem for sensitivity analysis. Okay? Okay, thank you. I will see you next time. Bye.